Hi guys, today we're going to be talking about a concept called cardinality, okay? So to begin this presentation, we're going to define what cardinality is. So let's just say that S is a set, right? Now, if there's exactly n distinct elements in set S such that n is an integer that is greater than or equal to 0, then S is a finite set, and n would then be the cardinality of S. And we call the cardinality of S with a brackets around it. That's how we denote it. So if a set is not a finite set, then we call it an infinite set. Now let's look at sets A and sets B. The two sets have the same cardinality if and only there exists a one-to-one correspondence between A and B. And this means that there exists a function between A and B that is both one-to-one and onto. So the way we denote A being equal, having the same cardinality as B, is A, cardinality of A equals cardinality of B. Now, if there exists a one-to-one function, not onto, from A to B, the cardinality is less than or equal to the cardinality of B, to which then we write the cardinality of A is less than or equal to B. So, next, let's go ahead and talk about countable sets. What exactly is a countable set? Well, a set is either finite or has the same cardinality as n is called countable. Now, if a set isn't countable, then it's called uncountable. Now, the mathematicians that came up with this concept probably weren't the most creative because it's quite literal. So we denote the cardinality of an infinite countable set with aleph null. This basically looks like this. I'm not a very good artist, so you're just going to have to bear with me. It looks something like this. So, I have an example for you guys. Let's show that the set of odd positive integers is countable. Now, to show this, we need to show that there's a one-to-one correspondence between the set of positive integers and the natural numbers. So let's consider this function, okay? So using 2, we're going to prove that there is a one-to-one correspondence, and to do this we must show that f of n is both one-to-one and onto. To see that the function is one-to-one, let's let f of n equal to f of m, which implies that 2n minus 1 is equal to 2m minus 1, which implies that m consequently is equivalent to m. And this shows that if there's any two elements that map to the same element, they must be equal, demonstrating that f in fact is one-to-one. Now, to show that f is an onto, we're going to choose an odd integer x, and by inspection note that x is 1 less than an even integer. Now, since every even integer can be denoted by 2k, then we see that every positive integer is then a possible value of f of n. Therefore, since f of n is both one-to-one and onto, because f of n is 2n minus 1, so consequently it would denote positive odd integer, then we have one-to-one correspondence, and therefore the cardinality of positive odd integers is equal to the cardinality of n, which is consequently equal to aleph null. Now, two other important examples of countable sets include the integers as a whole and rational. It's confusing to believe that odd integers and the integers as a whole have the same cardinality, but I can guarantee that this is actually the case. Now, on the other hand, if a set is not countable, then we call it uncountable. Remember what I said earlier about mathematicians not being creative? Now we're going to be talking about it. So basically, uncountable means that there doesn't exist a one-to-one correspondence between the set and the natural numbers. Now, sets such as the reals, which basically is short for real numbers, the irrational numbers, and complex numbers are uncountable. In addition, any interval of an uncountable set, such as the interval 0 to 1 for the reals, is consequently also uncountable. And then finally, let's talk about the Schroeder-Bernstein theorem, because I know you're going to be using it a lot in proofs and a lot of problems too. Schroeder-Bernstein theorem is actually spelled like this, in case you need to go ahead and look it up in your book later on. And it's an important theorem when dealing with cardinality, because what it basically says is that if there are A and B as sets, right, with A, the cardinality of A, having less than equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then it means that the cardinalities of both sets are equivalent. Now, this tells us that if there are two one-to-one functions, one that maps elements of A onto B, and another that maps elements of B onto A, then the cardinality of these two sets are in fact equal. Now, this is useful because it's important to note that it's often easier to find two one-to-one functions than it is to find one-to-one correspondence between two sets. So the Schroeder-Bernstein theorem is a very powerful tool in proving that two sets have the same cardinality. And this basically includes our presentation for today. We hope you enjoyed it. I had a lot of fun doing this. I hope you guys had a fun time listening to me. And maybe you learned a thing or two, maybe you didn't. Thank you.